This is 8.1.6, mass and energy. We're going to compare the energy involved in the three processes that you need to know about. One, which is radioactivity, which is your alpha, beta, gamma. Then fission, and then fusion. So we've got three processes. These are radioactivity, then we've got fission and fusion. Radioactivity, in terms of energy, is rather mild. For fission, you have to put a little bit of energy in to get fission started, and lots of energy come out as a result. So not much energy input, but we get lots of energy output. That's why we can use these in things like nuclear weapons or in nuclear reactors to generate energy. Then we've got fusion. For fusion, we need a large amount of energy input, and we get a huge amount of energy output. Now currently the trouble with fusion, and this has been for several years, for many years actually, is that often it takes more energy to start the reaction than what you get back as a result of the reaction. So it doesn't end up giving you any net energy gain as a result of doing fusion. One of the breakthroughs recently was that they managed to get a nuclear fusion reaction to output more energy than what they put in by using lasers. So if they can develop that further and have that become sort of commercial, then basically we'll be able to generate electricity for a lot less and a lot cleaner than we can do now. All right, for all of these though, there are some similarities. So we have a before and after. I'm going to use a couple of examples. Say if I've got two hydrogen isotopes that are separate. If I add their masses, we get some number. If I then make them do fusion, and I look at the total mass of the product of fusion, we have less mass than we did when they were separate. Some of that mass converted into energy. Let's look at another possible reaction where uranium does fission and becomes barium and krypton as a result. The mass of the uranium isotope before fission was greater than the sum of the masses of the barium, krypton, and the free neutrons that released as part of the fission process. So that difference in mass turned into energy. That's what we're getting at. So before any of these reactions happen, we've got more mass. And afterwards, we've got less mass. And we've got energy released. The reason why that works is, again, because Einstein said, according to E equals to mc squared, that mass and energy are interchangeable. They're basically the same thing. So mass can convert into energy, energy can convert into mass. So a mass that's lost by nucleons, which are protons or neutrons, turns into energy. And we call this the binding energy per nucleon. So we'll do one small example of this, which is the fusion example. And here we'll put deuterium. So before we've got two deuteriums, which are H21. So this is our before. And after, they join together and they're now bound together within an energy well. So if they've bound together, they've become something different. I should draw this as a double like this. This would be better. So here you got deuterium plus deuterium. That becomes 4,2 He plus some energy, because this has less mass than before. Okay, we'll start a new page. Our new title is the energy given out by fission or fusion. And we'll start with something called the atomic mass unit. Which is called U. So 1 U is the mass of one proton in carbon-12. Not the mass of one proton usually, but the mass of one proton in carbon-12. Because remember, a proton that's by itself will be more massive than a proton that has joined together with something else. It loses mass when it joins with something else. So 1 U is the mass of one proton in carbon-12, which is 12, it's 6 C. So normally, you know, or should know, that the mass of a proton is 1.67 times 10 to the minus 27 kilograms. But in carbon-12, it's slightly less. It's 1.66 times 10 to the minus 27 kilograms. So 1 U is 1.66 times 10 to the minus 27 kilograms. If we use E equals to mc squared on this number, we can convert from a mass into energy. And we can convert it to energy in joules, then we can also convert it to energy in electron volts, because we just do a conversion of units. So, in joules, this will give us 1.5 times 10 to the minus 10 joules. And in electron volts, it gives us 931.5 mega electron volts. So they all mean 1 U. So when we're using 1 U, we can work in joules, in mega electron volts, or in kilograms, whichever unit we choose to use. Questions may sometimes mix up units together, so you have to make sure that you convert to the correct units before you do your working. So hints for these questions. Number 1, write out the equation of the reaction. You should always write out the equation of the reaction. That will be used to guide you. Number 2, only use 1 unit throughout the whole process. Use only 1 unit throughout. And then number 3, if you need to convert to something else, do that at the end. Let's do an example of this. We're going to do the first fusion step in the sun. In the first fusion step, we're going to start with 2 hydrogen nuclei, which is just 1 proton. In the first fusion step, those 2 fuse together. But when they fuse together, instead of becoming 2, 2, so 2 nucleons, which are both 2 protons, one of those protons decay into a neutron and emit beta. So we write out the reaction. So the first fusion step in the sun. Proton plus another proton becomes, now you normally expect that to become 2 and 2 if they fuse together, but instead they become deuterium, which means that one of those protons has decayed, and if it's decayed into a beta plus, so that's 0 plus 1. And then it's also released an electron type neutrino and some energy. So plus some energy. Now, for these kind of questions, you will need to reference the formula booklet, because they will give you very, very precise values for the mass or the rest energy for each of these particles. If you don't use that, you will not be able to solve these problems. So in this case, I'm going to give you the numbers, but when you have this in an exam, reference the actual values that are in the formula booklet. So we start with the proton. So the proton is 1.00728 U plus another proton, which is 1.00728 U. And that's equal to, for deuterium, it's 2.0135 U. Then we've got our beta particle, which is 0.00055 U, plus our neutrino. Now the neutrino is 0.00000 U. It's so small that we can't even quantify it even in this situation. So our neutrino is 0.00000 U. It's so small that it rounds to 0. But it still has some mass. It's just that even in this case where things are very small, it's still very small compared to that. And then plus our energy. Now, if you were studying chemistry, you expect the masses to be equal. Whatever mass you had before should equal to whatever mass you have at the end. You can't gain or lose mass. But when it's nuclear, you can lose mass. Mass can just vanish and turn into energy. So, put this into your calculator, rearrange, and you should get E is equal to some very small number, 0.00051 U. Now you can convert that into any form you like. So let's say if I've asked you to give the energy in mega electron volts, you just sub in the mega electron value for U, 0.00051 times by 931.5 mega electron volts, and we end up with 0.475 mega electron volts. Okay, let's start a new page. Let's go on to binding energy now. So in both fission and in fusion, we've got more mass before, which turns into less mass after, but it also gives us some energy, plus some energy. So that change in the mass, that loss of mass, we call that the mass defect. And the energy is called the binding energy. But again, they're interchangeable because E equals mc squared. So the loss in mass is called the mass defect. And the energy is called binding energy. So we look at what this looks like again. Here's a proton plus, say, another proton. If they were to join together, then they're now bound in an energy well that keeps them together. So there's the energy well. Plus, it might make some other stuff as well. in general. So this isn't a specific example, but in general, there might be other stuff. Plus, we get some energy out. Now that energy corresponds to this energy well here. It's that potential well. So that energy that you got out of that reaction, you need to put that much energy in order to separate these two. But it doesn't always have to be based on separation, because this represents a fusion process, but the same could apply to a fission process. So for example, with uranium, when uranium undergoes fission, it separates into barium and krypton, and it gives us 3 neutrons. In order to go back to uranium, we have to input all the energy that was released back into it in order to make them join back together again. So it can work in both fission and in fusion. So we call that the binding energy per nucleon. And this binding energy per nucleon increases if you start from the lighter elements. If you start from hydrogen and work your way up to heavier element, it increases up until you get to iron. And when you get heavier than iron, then the binding energy per nucleon decreases a little bit. So heavier elements like to split apart, do fission, until they become iron. And lighter elements, they like to fuse until they become iron. That's what happens in stars. Stars stop fusing when they reach iron because there's no more energy left to give. Yeah? At that point, you have to put energy in to make the reaction happen, and you won't get energy out. So right, binding energy per nucleon. So, let's say, for example, in the previous case, which is what we did above, in the previous case, the energy is equal to 0.43 mega electron volts for 2 nucleons. So the binding energy per nucleon is 0.43 mega electron volts over 2. So therefore, the binding energy per nucleon is 0.43 over 2 mega electron volts. The bigger this number is, the better the nucleons stick together. So the more bound they are together. Hence why, again, iron does not like to fuse. It also does not like to do fission. So binding energy per nucleon, BEPN, tells you how well it sticks. I'll say how well the nucleons bind together. So the process of both fission and fusion, they both increase the binding energy per nucleon. I'm going to use some shorthands because it turns into quite a lot of words to start writing binding energy per nucleon over and over again. So there's a graph that describes this. We'll put the nucleon number on the x-axis. We'll put the binding energy per nucleon on the y-axis. We start at the bottom. We go up in kind of a straight line and then down a little bit. Like that. And I'll put a few things over here, some demarcations. So right at the top here we've got iron. So that's Fe, iron. All the way down at the bottom here, we've got hydrogen, H. Slightly higher than hydrogen, we've got He. That's 1, 1 and 4, 2. Over here, we've got uranium. So for example, uranium 92, 238 or 235. So all of the stuff on this side, they do fusion. And all of the stuff on the right-hand side towards iron, they do fission. And iron does not do any. It does not like to. So when we reach iron, we've become stable. Because iron has the largest binding energy per nucleon. Doing fusion or fission does not release energy. Rather, we have to put energy into it to make it happen, and we get nothing in return. And that is the end of 8.1.6.